So in this video, what I want to do is look at the generating function for Laguerre polynomials. So what am I talking about? What I'm talking about is the fact that if you look at the sum from n equals 0 to infinity, which is a power series, which has as its coefficients Laguerre polynomials, L sub n of x. This right here, it turns out, is equal to this function right here, 1 over 1 minus t, e to the minus tx divided by 1 minus t. So this function right here, if we take the Taylor series of this guy, then what we get are that the coefficients are Laguerre polynomials. And so that's kind of an interesting result. And this relationship right here ends up being really useful when we look at recurrence relationships with Laguerre polynomials. And so it's important to actually understand what's going here, understand what's going on here, and why it works. And so what I want to do in this video is prove to you that this expression right here is actually true. Okay, so how am I going to do that? How am I going to prove that this is true? Well, the way that I'm going to do it is I'm going to look at breaking down both sides into series. So I'm going to write the left-hand side as a series, the right-hand side as a series, and then show that the two are actually the same. Okay, so the first thing I'll do is write the left-hand side as a series. And so we know from last time that we can rewrite our Laguerre polynomials as a very nice series. And that series we saw last time was sum from k equals 0 to n choose k minus x raised to the k over k factorial, right? So this right here is just a way of rewriting this left-hand side right here. And if we wanted to, we could move this tn out in front, and then what we would have is this. We would have a sum from n equals 0 to infinity, a sum from k equals 0 up to n, and then we would have n choose k minus x to the k over k factorial times t to the n. So this is a series representation for our left-hand side of the equation. Now let's look at the right-hand side. So how are we going to redo this right-hand side? Well, we know what the Taylor series for an exponential function is, so let's start by writing that out. So we know that 1 over 1 minus t e to the minus tx divided by 1 minus t. We know that this right here is equal to 1 over 1 minus t, and then series from k equals 0 to infinity, 1 over k factorial times minus tx over 1 minus t raised to the k. Okay. Okay, so this is just substituting in the fact that we know that e to the x, the Taylor series for that is sum x to the n over n factorial. So here our x is this argument up here, so that's what's going on here. But you'll see we have this 1 over t out in front, or 1 over 1 minus t out in front, and this 1 over 1 minus t in here. And so I'm going to combine these real quick. I'll combine them, and so this whole thing right here will be just a sum from k equals 0 to infinity. We'll have minus tx to the k over k factorial, and then we'll have 1 over 1 minus t to the k plus 1. Okay, so we've got this right-hand side, or we've started getting this into the form of a series, but we still have this 1 over 1 minus t, whole thing raised to the k plus 1. Right, and so we know, so what are we trying to do? We're trying to make the left-hand side look like the right-hand side. And we know that our left-hand side looks like this. It's a series where t only shows up in the numerator. And so because of that suggests that in order for us to get this second sum, and in order for us to get all of our t's up in the numerator, we should get a series expression for this term right here, 1 over 1 minus t raised to the k plus 1. So how are we going to do that? Well, and I'll do it up in this corner. The way that we're going to do this is a little sneaky, but hopefully you remember. So First, let's recall the geometric series. So you'll recall that for the geometric series, what the geometric series tells us is that this sum right here, from n equals 0 to infinity t to the n, this guy is equal to 1 over 1 minus t, which is exactly what we want down here, except raised to the k plus 1. So how can we get this thing raised to the k plus 1? Well, one thing we could do, so one thing we could do is just, raise both sides to the k plus 1, but that's a little painful on the series side. But another way of doing it is by taking derivatives. So if we take a kth derivative of both sides, so dk dt to the k on both sides, what do we get? Well, and I'll just write this out right here. Dk dt to the k 1 over 1 minus t. Just 1 over 1 minus t. Okay. So yeah, what do we get here? Well, this right-hand term. Let's first look at evaluating this guy right here. So dk dt to the k 1 over 1 minus t. What's that equal to? Well, if we take k derivatives, what are we going to have? Well, we're definitely going to have 1 minus t raised to the k plus 1, right? Because for each derivative we take, this is going to go from being power minus 1 to minus 2 to minus 3, all the way down to k plus 1. So we're definitely going to have that. But with each derivative that we take, we're also pulling down some constant, right? We're pulling down first a minus 1, then a minus 2, then a minus 3. So we have so what do we have? We have ultimately a k factorial coming from the 1 times the 2 times the 3 times the 4, all the way up to k. And then we have a plus 1 and not a minus 1, because for each minus sign that we get from bringing down a minus 1 or a minus 2 from this power right here, we're also going to get another minus 1 from the chain rule, from the coefficient of this t right here. And so this right here is this right here is what we get by taking k derivatives of 1 over 1 minus t. Okay, so we know what this term is. What about this sum right here? How can we re-express this sum after we take t derivatives? Well, let's work on it. So dk dt to the k sum n equals 0 to infinity t to the n. Well, first off, what's this going to look like? Well, it's going to look like this. We're going to have a sum from n equals 0 to infinity. And then what happens? We're going to pull down an n, and we're going to pull down an n minus 1. And we're going to keep on pulling down coefficients all the way out to n minus k plus 1. Right? And it's going to be plus 1 because the last coefficient that we're going to have, so after we take k derivatives on this guy right here, we're going to have this being t raised to the n minus k. And so that means that the last coefficient of this thing right here has to be the one that was 1 higher than it. And so that's why we have the plus 1 here. T to the n minus k. Okay. So this is what this looks like. But notice here, though, that the first k terms of this series, the first k minus 1 terms in this series are going to be equal to 0, right? So if we have n equals 0, well, this whole thing's just multiplied by 0. If we have n equal 1, then this n minus 1 right here, that's going to be 0. For 2, it's going to be true. 3, it's going to be true, all the way up to k minus 1, right? Because if we have n equal to k minus 1 on this last term right here, then the k's and the 1's cancel. We get 0. So actually, that means that this sum right here, we don't have to start from 0, but we can start it from k. So we can do a sum from n equals k up to infinity. And then we're sort of leaving off all those terms at the start of the sum, which would have been equal to 0. So that's good. The last thing I want to do then, before I wrap this part up, is just, so this isn't the nicest way to write this out. It turns out, and you can check this pretty easily, that this coefficient right here is actually equal to, can actually be written as n factorial over n minus k factorial. And you can try this in a couple scenarios, and you'll see that it works out. It makes sense. So our What's the big takeaway here? So we see that this series right here is actually just this sum right here. So what have we managed to show in this part? Well, we've managed to show that 1 over 1 minus t raised to the k plus 1, right? Because this is what we initially were interested in. This guy right here is equal to 1 over k factorial. Right, so we have a k factorial right here. We divide it over. Then we have sum n equaling k up to infinity, n factorial over n minus k factorial times t to the n minus k. T to the n minus k. Okay, great. Run out of space, but all right, we're all good. So now that we have that expression right there, what I'm going to do is plug it back into this series right here, right? Because really what we're trying to do is show that these two series are the same. So let's plug this guy back in. So what happens when we plug it in? Well, we have our initial sum right here, k equals 0 to infinity, minus tx raised to the k over k factorial. And now we have our new expression. So we're going to get what? We're going to get another k factorial, 1 over k factorial. And then what are we going to have? We have sum from n equals k up to infinity, n factorial over n minus k factorial times t to the n minus k. Okay, great. So now let's just take this right here, move all the sums out, and try and make it look like this form right here as much as possible, and see how good we can do. So what happens when we do that? Well, first I'll pull out both sums. So we have a sum k equals 0 to infinity and a sum from n equals k to infinity. And then what? Well, notice that we have here, we have n factorial over n minus k factorial, and then we have another k factorial. And that right there is exactly the binomial coefficient, n choose k. Okay, so we have that. We also have minus x to the k over k factorial, which is exactly what we see right here. So that's good. We have minus x to the k over k factorial. The only thing left are these factors of t right here, but notice that we have t to the n minus k and t to the k right here. And so because of that, the k's cancel out and we're left with t to the n. And so this sum right here, or at least the coefficient of this sum on the right-hand side, is exactly equal to this coefficient of the sum here on the left-hand side. The only thing that's different between these two are, or at least from appearances, are what we're summing over. So here we have a sum from k equals 0 to n, and then n equals 0 to infinity. Here we have a sum from n equals k to infinity, and then k equals 0 to infinity. And so the question that we need to ask ourselves is, are these two sums summing over the same coefficients, or are they not, right? Because really what these sums are specifying are pairs of numbers n and k that we sum over. So this, and one nice way to visualize it is to sort of think of it as a grid. So if we have, say, k on this axis and n on this axis, then let's start with the left hand side. What values of n and k, because each of these arguments right here correspond to a single point in this n and k grid. Which points are these? Which values here are being picked out by this sum? Well, let's look at it. So we know that our sum is going from k equals 0 to n. So that means that you start from k equals 0, and then you go up to n, and you do it for all n. And so what that means is that along this line, n equals k, what this sum is doing is it's picking out all of the terms that start from k equals 0 and goes up to n. K equals 0 up to n, and it does that for all n. And so that's sort of the logic behind this sum right here, is that you're starting from an n equals 0, and then you're going, k equals 0 up to n, k equals 0 up to n. And then that sort of fills out this lower triangle in the nk grid. Okay, those are the points being specified by this sum up here. What about this other sum right here that we found? Well, let's look at it. So if we look at our n and k grid, what's happening? Well, our sum starting from n equals k, so n is being set equal to k, and then it's going out to infinity. So we set n equal to k, go out to infinity. And what you see is that this is actually exactly the same sum as it was in the first case. Both of these sums right here are specifying the same lower triangle in this nk grid. The only difference is that because we've written the sums a little bit differently, the order in which we're doing the sum is a bit different. So, so in this first case right here, we're sort of doing these vertical sums right here. But in the second sum, we're doing it a little different. We're starting we're doing these sort of horizontal sums right here. But the good news is that in the end, they both cover the same area in this nk grid, and because of that, we know that these two sums right here are in fact exactly the same, and hence this property up here is true. This property holds, and that means that we can put a box around it. Yep, perfect. So we've done it. So it took a little bit of work. We had to rewrite everything as a series. We had to do a lot of work on this 1 over 1 minus t raised to the k plus 1 term in order to be able to write this as a series. But at the end of the day, the arguments in these two sums are the same, and the coefficients that we look at, because of the way these two sums are written, are also exactly the same. And so this property holds. So I think I'll probably stop the video here. In the next one, I'm going to start looking at just how powerful this generating function can be, and especially with the types of recurrence relationships that you can derive using it. So I hope to see you in that video.